In this final video on numerical techniques, we're going to look at some of the pros and cons for all of the methods discussed. Remember throughout all of this that numerical techniques are very widely used. The reason for this is that many of the equations that arise in physics, economics, engineering, and other areas are insoluble equations. This means that we can't solve them algebraically. If we can't solve something algebraically, we need to use a numerical technique. So choosing the correct numerical technique is obviously a big issue. There are other numerical techniques not discussed in the A-level course, and not just for solving equations, but for solving things such as differential equations, or something that you haven't met at A-level, partial differential equations. Many types of differential equation are not soluble except by using numerical techniques. So numerical techniques are very, very important. To give a couple of examples, if you consider the equations of celestial mechanics to do with orbits of planets and satellites, many of these are insoluble by algebraic means. So when the Americans did the moonshot, they will have used numerical techniques to solve the equations in order to put Neil Armstrong on the moon. The flow of air over a Formula One racing car also gives rise to insoluble equations. And the list would go on and on. So when you're dealing with numerical techniques, you're dealing with a very important issue, and a technique that is used widely in the real world to solve real and important problems. In most A-level courses, there are 4 methods of solving the equation f of x equals 0 using a numerical technique. Simple iteration, the x equals g of x method, linear interpolation, interval bisection, and the Newton-Raphson method. Let's begin by looking at simple iteration, the x equals g of x technique. Quite simply, this is the worst method that we can use for finding a root numerically. It suffers from many problems. The only advantage is that iterations can be done very quickly on a calculator that has an ANS button. Most of the problems with this method center around the fact that it fails if the gradient is more than 1 or less than -1 anywhere near the root. But this failure can be quite complex in itself. It might fail completely, in which case this is obvious, but it might also go away from the root that we're looking for and find another one where the gradient does not suffer from this problem near the root. Another problem is that there can be many different arrangements. We have the equation f of x equals 0 to start with, and we have to arrange this into x equals g of x. And there's often many ways of doing this. It's very difficult to know at the outset which arrangement is going to find the root we're interested in. So we can end up doing a lot of algebra and not really making much progress. It only really converges quickly if the modulus of the gradient is much less than 1 in the vicinity of the root. This means the gradient being close to 0 in the vicinity of the root. It only really appears in courses because it is so unstable it can create interesting patterns and lots of discussion. Plus, of course, the fact that it can be quite quick to do when it does work. Once the equation is set up on the calculator, it's simply a case of pressing the equals button over and over. The next method we're going to look at is linear interpolation. The main advantage of linear interpolation as a method is that provided the curve is continuous, the method will always work. Unlike x equals g of x, it's not unstable. Provided the root is between our two values and the curve is continuous, we will work in and find the root. But as we've seen in the example, iterations can take time to do. Although we could set it up on a computer, the computer time taken would still be longer than it would for some of the other methods. Lots of different steps in the iteration and lots of calculations to do. So plenty of opportunity to make mistakes. And of course this adds to the fact that iterations take time to do. Even given that you can set this up as a computer program or a spreadsheet, there are still more calculations to do. So in a real situation where you might be setting up and solving lots and lots of equations, this method is still going to take longer for the computer to do and use more system resources than a faster method such as Newton-Raphson. But never forget the main advantage is that it will always work. Now consider interval bisection. Once again, provided the curve is continuous, this method will always work. It also has the advantage that we know, at least within one iteration, how many iterations are needed for a given degree of accuracy before we start doing the iterations. However, like linear interpolation, iterations can be time-consuming, and this is still the case if we set it up on a computer. Finally, let's look at Newton-Raphson. Like simple iteration, it is not always guaranteed to work. The Newton-Raphson method can fail, although it is greatly more stable than the simple iteration method. This method really only runs into problems if the gradient is very shallow near our approximation. If we look at this, we have a shallow gradient here, and the tangent takes us over to here. So when we take our next approximation, the tangent takes us much further away, and if we look at the fact there's a turning point here, the next gradient is going to take us away, a long way from the root here. So when it does fail, it fails quite spectacularly and quickly, and this is a good thing because we can see that it's failing very early on. As pointed out, we can see here that we've even gone past this turning point. If we go past a turning point, for example, just starting too far away, is another reason why the Newton-Raphson method might fail. So it's important when using this method to try to start it close to the root. However, the Newton-Raphson does have the following advantage. It is incredibly quick to compute and converges very rapidly when it does work. Because of this, Newton-Raphson is often the method of choice. It doesn't fail very often, like x equals g of x, and it is very, very rapid when it does work, especially compared to linear interpolation and interval bisection. However, if I can give you a personal experience, between years at university, I once worked for an engineering company. I had to write a program which solved some particular equations that they had. I wrote it using Newton-Raphson because it was my method of choice, and I thought it would work quickly. However, it failed on many of the sets of test data, and I ended up writing an interval bisection program. There is clearly a trade-off between methods. Newton-Raphson is spectacular when it does work. It gives answers to a very large number of decimal places after only a few iterations. And it really doesn't fail that often, despite my experience. The one method that I would discount is always the simple iteration method. It's far too unstable and really is not a very good method.